Hello, this is lab number 3 in physics 2212. It's a little table of contents to go over what we're going in our lab. So introduction, experimental setup, the Excel sheet, equation calculations, full script review, the error analysis, and the discussion at the end. So to start, the purpose of this lab is to better understand the magnetic fields through interaction by seeing the connection between distance and the field. Using this connection, distance can be used in the Biot-Savart law to find the magnetic moment of a given bar magnet. The fundamental equations and concepts are the Biot-Savart law, which is listed here, the distance-dependent magnetic field equation, which is listed here, and an overview of the results is mu equals 0.166 amps times meter squared, and then the n is negative 4.5429. The experimental setup starts with finding the magnetometer chip on the phone. So the system is the bar magnet, surroundings are everything else. The assumed model is the bar magnet as a magnetic dipole. The initial conditions of the magnet and the magnetometer on the phone. The goal of this is to basically find the chip. So moving it along the ruler stick with the magnet, moving it up in vertical and horizontal to find exactly where the chip is. So this is the Excel sheet, data sheet, and the calculations for the distance depending on the magnetic field formula and the linearization. So the linearized graph and the data from each magnetic field in the x direction. And this is the second part of the lab, which is the off-axis magnetic field distances. So basically, you have to find the d perpendiculars on the vertical and horizontal and average them. These are the calculations for mu using the formulas from the first slide. So the linearization right here is the inner slope value, which is negative 4.5429, and the k value, which is k equals 3.32 times 10 to the negative 8. Using r negative 1, you get the mu of 0.166 amps times meter squared. Calculations are listed here. So some observations from doing this is the magnetometer read 0 on the x-axis when the magnet was not close. The x component of the magnetometer would increase as the magnet got closer. The position of the phone would matter as moving it would change values. To avoid this, the phone and ruler stick were taped and elevated. The full script code. So first, there's a function for the magnetic field here, and these are the magnets at the origin with our mu mag, which is 0.1659 or 0.166. And this is the scale for the vectors that show the magnetic fields. So here are all the vectors coming off the axis, and here are all the perpendicular vectors. They're cyan, and the axis vectors are orange. Based off these observation points here, for putting in those vectors, you have to find the perpendicular vectors from the off-axis calculations. So with your average from the d perpendicular, distance perpendicular, which is 0.1663, you use that to make a magenta vector that shows the magnetic field of 45 degrees. This is the model with the axis vectors, the orange ones, and the perpendicular vectors are blue, and the 45-degree vector for the magnetic field, which is magenta, all the way up here. These were all scaled up by a factor of 1,000, and then more for the magenta vector, so you can see it on the simulation. Possible sources of error and assumptions for the lab. So nearby electrical equipment, plugging the smartphone, not properly aligning it, and metal and other materials that react with it. You can avoid this by doing it elevated and outside. The assumptions are that the magnet is a magnetic dipole. The magnetic field on the x direction increases as the magnet gets closer. When the magnetometer is far away, the magnetic field in the x direction is near 0. Here's some assumptions and observations. They match up. And lastly, there's some discussion questions. What if it wasn't oriented for magnetic north and we're at an intermediate angle with respect to Earth's magnetic field? The results would have been skewed due to Earth's effects on the magnetic field of the bar magnet from its own magnetic field. And for the second question, if there are two identical magnets stick together, If this happened, then that would just become one big magnet, and this would lead to smaller distance values. But overall, the magnitude, getting the magnitude and everything would be the same because the direction wouldn't change. And ending that discussion, that concludes my lab.